All right, in this video, I'm going to introduce a topic called partial fraction decomposition. It's the second of the two topics that your book inexplicably, that's a hard word to say, clumps together in section 5.7. Even though the topics aren't at all related, your book decides to throw them together and you learn them one after another. Anyways, partial fraction decomposition. The idea with that is consider these two integrals, the one in red and the one in green. Which one do you want to do? If I told you got to do one or the other, which one would you choose? And you might not be to the point where you're comfortable deciding which of these two is easier, but I think what you'll see by the end of this section is this one in green is exceedingly difficult, and this one in red is fairly easy. Let me show you. For this one in red, we really just have a sum or difference of these three different terms, and sums and differences of terms work out really nicely with integrals. We can just think about this as the integral of the first one minus the integral of the second one plus the integral of the third one. Furthermore, we can treat this 3 and this 4 that are up in the numerators here as constants. You can think about this second term as 3 times 1 over x plus 3. And you can think about this third term as 4 times 1 over x. And with those two changes, we can rewrite this integral as these three different integrals. And I think each of these three are pretty manageable, using the fact that the derivative of the natural log of x is 1 over x, or maybe a better way to state that the antiderivative of 1 over x is 1 over the absolute value of x. I think we could figure out all three of these. If you really wanted, you could use a u substitution on this one. But as I've mentioned before, you'll get to the point pretty quickly where you can do this without a u substitution. If you recognize that the derivative of the natural log of the absolute value of 2x plus 1 would almost be this, right? The derivative of the natural log of 2x plus 1 would be 1 over 2x plus 1, but then I wouldn't be done. I'd have to take the derivative of the inside part, chain rule, and the derivative of 2x plus 1 is just 2. So if I were taking the derivative of this, I'd get almost exactly what you see here, except with an extra 2. And I don't want that extra 2, so I better multiply this thing by 1/2 so I don't have that extra 2 when I take the derivative. Similarly up here, I could say that the derivative of the second term, leaving the negative 3 constant out in front, is almost, in this term it's going to be exactly, the natural log of x plus 3. But then I got to worry about, wait a minute, if I were taking the derivative of this, I'd have 1 over x plus 3 times the derivative of x plus 3. Oh, good. The derivative of x plus 3 is just 1. So there's no accounting for that I have to do here. What it comes down to is the coefficient on the x here is just a 1. The coefficient on the x here is a 2. So because the coefficient on the x here is a 2, we need this extra 1/2. But you don't have to memorize any of that stuff. Just think about, what would the derivative of this be? Oh, it would be exactly this? Cool, then I'm done. What would the derivative of this be? Oh, it wouldn't quite be this. I need this 1/2 to make things all balance. Finally, this last term, I got the derivative of 1 over x is the natural log of the absolute value of x. I tack on my plus c, and I'm done. Right? That's it. If you want to clean this up, you can. But even that is kind of unnecessary. You could stop up here. The point is, this problem is not that bad at all. This is something that you can handle. Unfortunately, this problem over here in green is not nearly so simple. In fact, this problem is exceedingly difficult. You might think you have a couple ideas of how to attack it just by looking at it, but I bet you don't. A u substitution isn't going to help you off the bat. Integration by parts, also no help. You're like, oh, I'll just do some algebra. I'll make this 3x squared divided by this whole mess, plus this second term over this whole mess, plus 12 over this whole mess. That won't work either. This little natural log trick we do, it turns out that it only works out nicely if we have linear factors. If this instead said the natural log of 2x cubed plus 7x squared plus 3x, I couldn't just make it balance by putting a 1/2 here, because when you use the chain rule, it would introduce new x's, and just trust me, things would blow up. This method would not work on this problem. We need a whole new topic, which we haven't learned yet in this class, called partial fraction decomposition to attack this problem. And now you might be kind of confused, like, wait, okay, so you're teaching me a new method for this green problem. Why'd you even bother telling me about this red problem? Like, what's the connection between the two of these? Turns out these two things are the exact same. All right, that's kind of surprising, but this expression is identical to this expression over here. What you see in red is the same as what you see in green, so the integral of green is this exact same answer that we have over here. How can that possibly be? How can I change green into red? Well, changing red into green isn't too bad. Changing red into green, you can check this. We just have to get a common denominator between these three terms. So this first one, we'd multiply the top and the bottom by x, and then by x plus 3. And this second one, we'd multiply the top and the bottom by x and then 2x plus 1. And this third one, we'd multiply the top and the bottom by 2x plus 1 and x plus 3. And then we'd have the same denominator on the bottom, the product of x, x plus 3, and 2x plus 1. And guess what? The product of x, x plus 3, and 2x plus 1 is exactly 2x cubed plus 7x squared plus 3x. And when you put all three of these terms over that same denominator and you combined like terms, what you'd end up in the numerator is exactly what you see here. I'm telling you, trust me, I did it. The stuff in green is exactly the same as the stuff in the red. The way I made these examples is I started out with red and I changed that into green. And going from red to green isn't too bad. The bad news is going from green to red is difficult. And going from green to red is this technique called partial fraction decomposition. And it's what we'll spend the rest of the video on. And by the way, partial fraction decomposition, sure, you're learning this in a calculus class, but it's not a calculus topic. I'm done with the calculus. The only calculus I'm going to talk about with partial fraction decomposition is making the argument that red is easier to do calculus on, to kind of create a verb, than green is. Everything we're going to be doing with partial fraction decomposition is just algebra. It's a bunch of algebra to change this question into this question, because this question we can't do calculus on, but this one, as we've already demonstrated, we can. So how do you do partial fraction decomposition? Step 1 is to factor the denominator. So what I'm saying here, this 2x cubed plus 7x squared plus 3x, we can factor that. In this specific case, all three terms have an x in them, so I can pull out that x, and what I'd have left would be 2x squared plus 7x plus 3. And then that 2x squared plus 7x plus 3 can be factored into linear terms. There's lots of different ways you can do this. One way or another, you'd want to be able to get that this is 2x plus 1 times x plus 3. Easier to check than to come up with in the first place. 2x times x gives me the 2x squared. 1 times 3 gives me the 3. And then the O and the I in FOIL, the 2x and the 3 gives me 6x. And the 1 and the x gives me 1x. And 6x plus 1 more x gets me this 7x. The point is, this third degree polynomial that we started out with in the denominator can be factored into these three linear terms. They're called linear terms because they don't include any x squareds in them. They're just x's and constants. And when you can factor into three linear terms, these problems don't work out too badly. We'll see in the next video what you do if you get anything that's irreducible here when you can't factor into linear terms. But for now, let's suppose you can factor the denominator into linear terms. We did that here. Here are three linear terms. Step 2. Step 2 is to rewrite the original expression, so I'm talking about this entire fraction right here, as a sum of fractions, so something plus something plus something, where we have constants up in the numerator and the factors from step 1 down in the denominator. That's a lot harder to write than it is to do. All I'm saying is when you factor this into three different linear terms, you're going to rewrite this as a over the first term, maybe x, and then b over the second term, 2x plus 1, and then c over the third term, x plus 3. And if this factored just into two terms, then you just have an a and a b. If this factored into four different linear terms, you'd have an a, b, a c, and a d, and so on. You factor this into linear terms, and then you rewrite this as the sum of these different fractions where the factors are down on the bottom and just constants a, b, and c are up on the top. So this new form that I came up with, I'm going to set that equal to the original expression. My original expression up here, 3x squared plus 28x plus 12 divided by 2x cubed plus 7x squared plus 3x is what I want to put here. And you might be like, wait, that's not exactly what you put there. The top looks exactly like what you put there, but the bottom looks different, right? All I'm doing on the bottom here is I'm writing the factored form of the denominator. So the denominator started out as 2x cubed plus 7x squared plus 3x. But in step 1, we figured out that's the same as x times 2x plus 1 times x plus 3. So I can write x times 2x plus 1 times x plus 3 down in the denominator here. That's step 2. Step 3 is to clear the denominator. It's kind of a satisfying step. What I'm saying here is we're going to multiply both sides of the equation by x times 2x plus 1 times x plus 3 by these factors that we figured out that appear on both the left-hand side of the equation and the right-hand side of the equation. So I'm going to multiply both sides of the equation by that stuff. On the left-hand side, if I multiply by x and 2x plus 1 and x plus 3, it'll all cancel out. And all I'll be left with is what was up top, the 3x squared plus the 28x plus the 12. But on the right side, things are going to be a lot more confusing. Because if I multiply by x times 2x plus 1 times x plus 3, that product has to hit each of these three terms. So I have to multiply it by this guy, and then I have to multiply it by the second one, and then I have to multiply it by the third one. Well, if I take this x times 2x plus 1 times x plus 3 and multiply it by the first guy, the x, think about all three of those factors going up top. the x and this x will cancel, so all I'll have left will be the 2x plus 1 and the x plus 3 and the a. In this second term, if I took x times 2x plus 1 times x plus 3 and kind of put it in the top of this fraction, then the 2x plus 1s would cancel. There's one on the top and one on the bottom. And what would be left up top would be this x and this x plus 3 and the b. And then in this third term, if I put all three of these factors up top, the x plus 3s this time would cancel, and I'd be left with an x, a 2x plus 1, and the c. It's easy to get lost in the steps, but what I'm trying to justify is how we get to this equation here. Right? This equation will allow me to figure out what a, b, and c are equal to. And if I could find out what a, b, and c are equal to make this equal to this, well, then what I've done is I've rewritten the left-hand side of the equation in something that looks a lot different, that looks like a sum of a bunch of different fractions, that looks a lot like what we have in red over here. So in order to get this to look like it looks in red, all I got to do is solve for a, b, and c. I can solve this equation for a, b, and c. And you're like, that's going to be a nightmare. It's not as bad as maybe you'd think. My fourth step is just to solve for the constants. In this case, they're a, b, and c. But remember, they could just be a and b if you only had two factors. They could be a, b, c, and d, so on. In this case, I have three constants, a, b, and c. And I'm going to solve this equation to figure out what they're equal to. And you're not quite sure how to do that, but it's going to work out kind of nicely. Just trust me. First thing you want to do is get rid of all of your parentheses. That's going to involve a lot of foiling. 2x plus 1 times x plus 3 is 2x squared plus 7x plus 3. I guess I have that written up here. So I have 2x squared plus 7x plus 3 times a. If I take that a and distribute it through, I get 2ax squared plus 7ax plus 3a. Didn't quite follow that? That's okay. We'll get another chance to do it again. For this second term here, x times x plus 3 times b. Well, x times x plus 3 is easy. Just take the x and distribute it through. You get x squared plus 3x. But if you want to multiply b times that stuff, then you get bx squared plus 3bx. In this third term, you take the x and multiply it by the 2x plus 1, and you get 2x squared plus x, but you have to multiply the c through, so you get 2cx squared plus cx. And so getting rid of all these parentheses yields this line right here. And you're like, I don't see how I'm getting anywhere closer to the answer. Well, what we're going to do here is if 3x squared plus 28x plus 12 equals this whole mess, then let's focus on just the x squared terms. I have 3x squareds on this side of the equation. On this side of the equation, I got 2ax squared, bx squared, and 2cx squared. I have to have the same number of x squareds on this side as this side if the two equations are the same. So what that tells me is that the 3 must be the same as 2a plus b plus 2c. So based just on my x squared terms, I know that 3 must be the exact same as 2a plus b plus 2c. You could call this equating the coefficients. The coefficients on x squared on this side of the equation have to be the same as the coefficients on x squared on this side of the equation. So the 2a, the b, and the 2c have to be the same as the 3. Similarly, I can equate the coefficients on my x's. I have 28x over on this side, but on this side I have 7a times x, and I have 3b times x, and I have c times x. So what that tells me is that 28 must be the same as 7a plus 3b plus c. And then finally, my constants have to be the same. I can relate together the coefficients on the ones if you want to think about it that way. It tells me that 12 must be the same as, let's see, where are my terms without x's on them? Oh, I got a 3a here. What about b's? Oh, I don't have any. What about c's? I don't have any. The only constant I have is this 3a here, so 12 must be equal to 3a. What I have here is what's called a system of equations. A system of equations is what you learn how to solve in a linear algebra class. The good news is the systems we'll solve in this class won't be too difficult. All we got to do is figure out what a, b, and c must be equal to. Well, from this bottom equation here, I know that a must be equal to 4. Why? Because if I divide both sides of this equation by 3, I get a equals 4. If a equals 4, I can plug that up in these equations, and I can be like, well, 7 times 4 is 28, and I can subtract 28 from both sides of this equation and get 0 is equal to 3b plus c. Right? I'm going to take the a equals 4 and put that in here. That gives me 28. I'm going to subtract 28 from both sides of the equation, and I'll have 0 on the left and 3b plus c on the right. Similarly, if I change all my a's into 4's up here, I get 8 from this term. If I subtract 8 from both sides, I get negative 5 on the left, and I get b plus 2c on the right. Now, instead of having 3 equations, I only have 2 equations, and I can solve these 2 equations. There's lots of different ways you can do it. There's an easier way and a harder way. The more natural way that people do it is actually a little bit harder. The more natural way people do it is they're like, well, why don't I just solve this for C and then substitute that into the other equation? And that'll work out fine, although in certain instances that can be really rough to do. A more clever way to do it is to add your equations together. So take this bottom equation maybe and multiply it all by -2. So if I leave the top equation completely alone, I get -5 equals b plus 2c. And if I take this bottom equation and multiply everything by -2, 0 times -2 is still 0. 3 times -2 is -6b. And c times -2 is just -2c. You might be wondering why I chose -2. It's because I knew that in the next step, I was going to add my equations together. So I wanted to choose something to make one of these cancel out. So if I add these out, all my c's will go away here. Note I could have multiplied the top equation by -3 instead of multiplying the bottom equation by -2. If I had multiplied these all by -3, I would have had -3b, which when I add the equations together would cancel out with this positive 3b. At any rate, if you add these equations, -5 plus 0 gives you -5. B plus -6b gives you -5b. And then 2c and -2c gives me nothing. That was the whole goal, to get rid of one of the variables. If -5 equals -5b, divide both sides by -5, and you get that b equals 1. And the second you know that b equals 1, you can plug that in to solve for c. You can plug it into any equation that you want, but maybe this would be the easiest one. If I change all my b's into 1s here, I get 3 plus c equals 0. So therefore c must be equal to -3. Now that I know A, B, and C, I know what goes in place here, here, and here. What I'm saying is the A is the 4, the B is the 1, and the C is the -3. I can rewrite this as, instead of A over X, 4 over X. Instead of B over 2X plus 1, 1 over 2X plus 1. And instead of C over X plus 3, I could write it as -3 over X plus 3. What I've shown through this really complicated process, which is what's called partial fraction decomposition, is that this original expression that I was given up here in green is equal to A over X, B over 2X plus 1, C over X plus 3. We're playing the role of A, B, and C are these numbers. In other words, my claim is that what I have here is the exact same as what I was given here. And the good news is that what I have here is something we already took care of up here, right? There's the 4 over X. There's the 4 over X, 1 over 2X plus 1, and -3 over X plus 3. 1 over 2X plus 1, and -3 over X plus 3. You might be like, wow, that was a lot of algebra. Am I really expected to do all of that? Well, yes, I guess. But here's something that I can tell you to kind of ease your mind a little bit. I want to test the topics of calculus and less the topics of algebra. So what I will always do when I test you on this is I'll give you the denominator already factored, so you won't have to do this first step. I would start you out with this and ask you the question, hey, what's the integral of this? And then you'll be like, oh man, partial fraction decomposition, and you'll have to solve for A, B, and C similar to what we did here. It's also worth pointing out that if the denominator is a product of 3 terms, it's pretty challenging. With the A and the B and the C and the algebra, it gets kind of hard. Maybe for the sake of a test, I just make it the product of 2 different terms, so it's just an A and a B to make your life a little bit easier. Or if we do 3, I choose the numbers very carefully to make sure all the algebra works out nicely for you. The bad news is on the homework, I know there's not very many homework problems because they take forever, but I know they start you out with the denominator in its unfactored form as opposed to its factored form. So that's why in this video I wanted to show you the first step where you factor the denominator. Hopefully this will work as a good roadmap for the partial fraction decompositions problems. However, there's one more special case I have to show you. But the good news about the special case is it's going to follow more or less these same 4 steps. So if these 4 steps make sense, I think the next video where we tackle kind of the special case won't be as much to add on to.